Hello my friends, and welcome back to the You Can Do TV channel. Haggi steel wire rope follows a highly controlled, process-driven manufacturing system that emphasizes technical precision, durability, and compliance with international standards. Production starts with carefully selected high-carbon steel rod, which is chemically analyzed to ensure consistent mechanical properties. The rod undergoes surface preparation and multi-stage wire drawing, where diameter reduction, tensile strength, and surface integrity are tightly monitored. Intermediate heat treatment is applied to optimize fatigue resistance and ductility while maintaining high tensile performance. Depending on the application, the drawn wires are either galvanized or left bright. Galvanizing is executed under controlled conditions to achieve uniform coating thickness, strong adhesion, and long-term corrosion protection. Individual wires are then assembled into engineered strand constructions, including 6-strand, 8-strand, compacted, rotation-resistant, and triangular strand designs. Lay length, strand geometry, and compaction ratios are selected to manage torque balance, load distribution, and bending fatigue. For deep-level shaft mining, hoist ropes are designed for extreme cyclic loading and long vertical travel distances exceeding 3,000 meters. Surface mining ropes prioritize abrasion resistance and extended service life, while offshore ropes are engineered for dynamic loading in corrosive environments. Continuous inspection, mechanical testing, and final rope break tests ensure consistent performance and safety. Heavy lifting operations commence with the careful transport of colossal anchor chain links from the storage yard to the vessel. Steel cables are meticulously twisted and interwoven to form these enormous links, with each strand precisely aligned and tensioned before being spun together. The result is a single, exceptionally strong chain, engineered to withstand extreme loads while maintaining uniform durability and flexibility, essential for heavy lifting and mooring applications. Rigging crews coordinate every movement with precision, controlling swing radius, lifting speed, and alignment to eliminate shock loading. Using heavy-duty cranes equipped with certified slings, hooks, and spreader beams, the massive chains are lifted onto the ship's deck with careful monitoring of speed, angle, and stability to prevent twisting or impact. Once positioned, each link is accurately placed in its designated location, ready for splicing, welding, and final installation. This phase is critical, ensuring the integrity and readiness of the giant chain assemblies for operational deployment. When the heaviest loads and extreme conditions challenge conventional lifting, United Offshore Services delivers unmatched steel rope solutions. United Offshore Services provides engineered solutions for ultra-heavy lifting and offshore operations. Steel ropes are manufactured to exacting standards, ranging from 6 mm to 500 mm in diameter, and are capable of handling extreme lengths, heights, and depths. Only manufacturers guaranteeing the highest steel quality are selected, ensuring each rope delivers maximum strength, durability, and safety. Each sling undergoes rigorous inspection, measurement, marking, and certification, complying with international standards and guidelines. The specialized grommet machine handles ropes, weighing up to 150 tons, with circumferences up to 300 meters, maintaining precise length tolerances and consistent quality. Traction and load testing reaches up to 300 tons to detect any irregularities, while shackles and ancillary lifting equipment are similarly tested to prevent failures under extreme conditions. After thorough cleaning and corrosion protection, ropes are stored in a highly organized system that allows rapid access for immediate deployment. Advanced technology and precise workmanship ensure safe, reliable, and certified lifting solutions for marine, offshore, and industrial applications worldwide. Anchor chain installation works are a critical repair operation to restore the safety and operational reliability of offshore structures and marine vessels. Individual chain links are first accurately aligned and mechanically connected to restore the continuous load path. Specialized welding procedures are then applied to permanently rejoin the links, ensuring full penetration and strength equal to the original material. Each weld is inspected, using non-destructive testing to confirm structural integrity. Once approved, the repaired chain is lifted, guided, and installed into position using cranes and tensioning equipment. Proper seating, alignment, and load testing ensure the anchor system operates safely under demanding marine conditions. The BMT Repairs Bow Thruster Replacement Operation showcases precision marine engineering and coordination at its finest. The procedure commences with the vessel safely docked in the shipyard, where the maintenance crew begins the removal of the damaged bow thruster unit. Heavy-duty cranes and specialized lifting frames are deployed to extract the old assembly from its tunnel housing. Once removed, the seating area and thruster tunnel are thoroughly cleaned, inspected, and prepared for installation. A newly fabricated bow thruster is then carefully positioned and aligned within the tunnel, using laser alignment tools to ensure optimal thrust efficiency. Welding and sealing works follow, restoring the watertight integrity of the hull structure. After mechanical and electrical connections are completed, the system undergoes comprehensive operational testing, including thrust direction, noise, and vibration checks. The 2,800 bars ultra-high-pressure water jet blasting machine is engineered for intensive vessel cleaning and surface preparation in marine and offshore environments. Operating at extremely high pressure, it efficiently removes marine growth, old coatings, rust, and contaminants without damaging the steel substrate. The system reduces abrasive consumption, minimizes waste generation, and improves environmental performance. Its robust pump unit, durable hoses, and precision-controlled nozzles ensure consistent cleaning results, high productivity, and reliable operation during demanding ship maintenance and dry dock applications. The AW-M6 magnetic crawler is a specialized robotic system for FPSO and oil tanker hull cleaning. It removes marine growth above and below water using magnetic adhesion, ensuring efficient cleaning without damaging existing protective coatings on large marine vessels. The Dockboy Ship Preparation System is a remotely controlled cleaning vehicle engineered for efficient and safe hull maintenance in the maritime industry. Designed to operate on hull bottoms and vertical surfaces, it provides a working height range from ground level up to 9.35 meters, enabling thorough surface preparation without scaffolding or manual access. With operating pressures reaching up to 3,000 bar, Dockboy effectively removes marine growth, coatings, and contaminants while maintaining precise control. Its compact vehicle height of only 1.26 meters allows access to confined dock areas and tight clearances. By combining high-pressure performance with remote operation, Dockboy improves productivity, enhances operator safety, and delivers consistent surface quality prior to inspection, repair, or recoating operations. Crane barge Ignatius Versus undergoes a comprehensive maintenance operation focused on hull cleaning and surface protection. High-pressure water jets are used to remove marine growth, algae, and accumulated biofouling from the steel surfaces without causing structural damage. This cleaning process restores the hull to bare, sound material and prepares it for coating. After inspection and surface drying, a new marine-grade protective paint system is applied to prevent corrosion and extend service life. The combined use of water jet cleaning and repainting ensures improved durability, operational efficiency, and long-term reliability in harsh marine environments. The dry docking of the bulk carrier Santa Maria is a methodical, step-by-step engineering operation aimed at restoring structural condition and extending service life. After precise alignment over keel and side blocks, the dry dock is gradually dewatered, allowing the vessel to settle evenly and safely. Once fully dry, the hull, rudder, propeller, and sea chests are exposed for close inspection. High-pressure water jetting removes marine growth and old coatings, preparing steel surfaces for assessment. Thickness measurements and corrosion checks identify areas requiring steel renewal or repair. In parallel, mechanical components such as valves, stern gear, and steering systems undergo overhaul. Repainting is a critical phase. Following surface preparation, approved anti-corrosion primers and anti-fouling coatings are applied under controlled conditions to protect the hull and improve hydrodynamic performance. The process concludes with refloating, functional tests, and final class inspections before Santa Maria returns to operational service. Using the OERT ZENE 500-30, ship hull cleaning becomes a precise and controlled preparation step for anti-corrosion work. High-pressure water jets effectively remove marine growth, old coatings, rust, and salt deposits without abrasive media, preserving the integrity of the steel surface. This water jetting process creates an ideal surface profile for new protective coatings, improves adhesion, and extends coating service life. It is an efficient, environmentally responsible solution for professional ship maintenance and corrosion prevention. NASA engineers completed a major structural integration milestone for Artemis II by joining the SLS core stage forward assembly with the 130-foot liquid hydrogen tank. Using precision alignment tools, teams installed 360 high-strength bolts to form the primary load-bearing connection. This mating completes 4 of the 5 core stage elements, leaving only the engine section to be added. The operation validates structural interfaces, alignment tolerances, and assembly procedures at NASA's Michoud assembly facility. In February, NASA and Boeing completed the thermal protection of Artemis III's liquid hydrogen tank at Michoud. Using a robotic tool, 107 feet of spray-on foam were applied in 102 minutes, forming the yellow base that UV rays tan to NASA orange. The 212-foot tank feeds 4 RS-25 engines. Technicians at NASA Kennedy's Vehicle Assembly Building carefully lifted the fully assembled Artemis II SLS core stage, 225 feet tall, using massive cranes. The stage was moved from High Bay 2 to the transfer aisle, where final preparations took place before integration with the twin solid rocket boosters. This efficient stacking process supports upcoming moon missions, beginning with the Artemis II test flight, streamlining assembly and ensuring precise alignment for launch readiness. At NASA's Marshall Space Flight Center, subscale booster motor testing is advancing future SLS propulsion technology. Engineers successfully fired a 24-inch test motor in the East Test Area, generating over 82,000 pounds of thrust. The test supports evaluation of alternative nozzle and insulation materials for upgraded booster designs planned for SLS missions beyond Artemis 7. As the Space Shuttle era concluded in 2011, NASA shifted its focus beyond low Earth orbit toward deep space exploration, beginning with a return to the Moon. Thousands of concepts were evaluated with industry partners to define a rocket that balanced power, safety, and reliability. The result was the Space Launch System, designed to carry astronauts and cargo. For Artemis I, SLS can deliver 59,000 pounds to the Moon. In the relentless pursuit of more efficient and sustainable space exploration, every kilogram saved on a rocket's upper stage translates into significant energy reductions and a smaller environmental footprint. The ProComp project embodies this vision, demonstrating an innovative method for producing large-scale liquid hydrogen fuel tanks for next-generation launch systems. The German Aerospace Center developed a thermoplastic liquid hydrogen tank demonstrator, employing automated fiber placement and a differential design to optimize manufacturing efficiency, dust-free joining, equipment installation, and quality assurance. The tank is composed of two integral sections. Construction starts with a smaller dome, built layer by layer by a robotic system depositing 3 pre-preg tapes per pass. Thermal imaging and laser line projection ensure precise placement in real time, capturing 3D surface data for digital twin integration. The second section integrates the main tank structure, with skirts connecting to the rocket's upper stage and lower assembly. Fibers are oriented in multiple directions, with up to 16 pre-preg layers in critical areas. Pole flanges and an anti-sloshing device are installed, with the propellant management system functioning as both gallery and welding jig. The dome is inserted and joined via continuous ultrasonic welding, where vibration-induced heat applied under pressure and controlled cooling ensures reliable assembly. This demonstrator proves that integrated quality assurance, differential design, and thermoplastic optimization can simultaneously reduce weight and cost, establishing a foundation for future European launchers and potential industrial applications. At NASA's Marshall Space Flight Center, technicians flipped the 5-foot 800-pound Orion stage adapter to install a critical diaphragm. This component connects the Orion spacecraft to the SLS rocket's interim cryogenic propulsion stage and prevents launch gases from entering the spacecraft, ensuring safety for Artemis II. At NASA's Michoud Assembly Facility, the Artemis II core stage reached a critical propulsion integration milestone with the installation of all 4 RS-25 engines. Each engine was individually lifted, aligned, and mated to the thrust structure using precision handling equipment, with strict control of tolerances, load paths, and contamination. Mechanical attachment, propellant feedline connections, Avionics interfaces and thrust vector control systems were verified during installation to ensure full compatibility with the core stage structure. The RS-25 engines are configured to operate in a clustered arrangement at the base of the 212-foot-tall core stage. During launch, 4 engines will fire for approximately 8 minutes, delivering more than 2 million pounds of combined thrust to propel the vehicle through ascent and into low Earth orbit. This phase validates propulsion system integration and structural readiness for flight. Program management, systems engineering and technical authority are provided by NASA's Marshall Space Flight Center. The 22AF transformer coil winding machine from UPI is designed for high-precision winding of round transformer coils with integrated coil flattening capability. The system uses a servo motor-driven mechanism to control winding speed, tension, and layer positioning with exceptional accuracy. During operation, the coil is wound uniformly and then flattened in line to achieve consistent geometry and optimal packing density. This controlled flattening improves electrical performance, reduces air gaps, and enhances thermal efficiency. The machine supports repeatable production with stable tension management, accurate turn counts, and smooth acceleration profiles. Its robust construction and automation make it well-suited for medium and high-volume transformer coil manufacturing environments. Workplace safety starts with the foundation, protective footwear engineered to withstand extreme conditions. At the core of these shoes are steel and aluminum toe caps and steel midsoles, designed to absorb impact, resist compression, and shield the foot from industrial hazards. Production begins with premium steel or aluminum billets, precisely cut and preheated in controlled furnaces to achieve uniform malleability. High-tonnage forging presses shape the metal into the curved, ergonomic profiles of toe caps, while hydraulic stamping and pressing form the robust steel midsoles. CNC machining refines dimensions, ensuring tight tolerances and perfect fit, while surface treatments and coatings enhance corrosion resistance. Specialized paints are applied evenly, followed by controlled drying to achieve a durable, protective finish. Each component undergoes meticulous inspection, including hardness tests, dimensional checks, and visual surface evaluations, ensuring consistency and compliance with international safety standards. Automation, precision engineering, and rigorous quality control converge in this process, transforming raw metal into vital safety components that protect workers across industries, from construction and mining to manufacturing and logistics. Corrosion Fasteners uses advanced machinery for precision manufacturing, including automatic screw thread rollers, rivet presses, coil nail winding systems, bolt and nut threading machines, CNC pin fabrication, and heat treatment furnaces. Multi-axis grinders and automated inspection systems ensure durability, accuracy, and high-quality fasteners across screws, nails, bolts, clamps, and pins. Welcome to Hydrodrunen, a leader in aluminum production, where cutting-edge technology, precise engineering, and sustainable practices converge. The process begins in the recycling unit, the cornerstone of environmentally responsible manufacturing. Scrap aluminum from various sources is carefully collected, sorted, and processed to create high-quality billets. This stage ensures that recycled material maintains the required alloy composition for downstream extrusion and fabrication, preserving both material integrity and resources. The recycling unit embodies Hydrodrunen's commitment to sustainability, transforming waste into premium raw material while reducing environmental impact. From the recycled billets, the material moves to the extrusions unit, where advanced presses shape aluminum into precise profiles. Hydrodrunin operates 8-inch and 10-inch extrusion presses, capable of producing a wide variety of cross-sections with high dimensional accuracy. After extrusion, profiles are processed using CNC machining and curtain siders, allowing for precise drilling, cutting, and shaping according to strict customer specifications. Quality control checks at this stage ensure that every extrusion meets exact tolerances, with thorough inspections for surface finish, strength, and uniformity. The production then transitions to the pole products line, dedicated to manufacturing poles for street lighting, utilities, and industrial applications. The process begins at the conifying machine, which shapes each pole to the correct taper. Poles are then drawn on the pulling bench, elongating the material for structural uniformity, and straightened on the straightening bench to correct any deviations. Doors and access panels are precisely cut using the door cutting machine, assembled at the door lock assembly station, and welded using both a robotic welding system and a specialized corner welding unit, ensuring consistent strength and precision in every joint. After shaping and assembly, poles undergo finishing processes, including sawing lines, milling machines and brushing machines, refining surfaces, and eliminating imperfections. The final step is the coating line, where protective and decorative finishes are applied, delivering durability, corrosion resistance, and visual appeal. Throughout the entire production process, Hydrodrunin combines advanced automation with skilled human oversight. Every stage, from recycling to extrusion, machining, pole fabrication, and coating, is carefully coordinated to guarantee quality, efficiency, and safety. The result is a comprehensive range of high-quality aluminum products that meet stringent international standards, ready for infrastructure, industrial, and commercial applications. Hydrodrunin exemplifies the integration of innovation, precision, and environmental responsibility, establishing itself as a benchmark for modern aluminum manufacturing, producing products that are as reliable as they are sustainable. Aluminum extrusion is a highly controlled industrial process that transforms raw aluminum billets into precise profiles for structural, architectural, and industrial applications. Production begins with a 16-billet cutting machine, which prepares billets to exact lengths before they enter the billet preheating furnace, where temperature is carefully regulated to ensure optimal metal flow. At the same time, molds are conditioned in a dedicated mold preheating furnace, guaranteeing dimensional stability and surface quality during extrusion. The core of the operation is the 6,000-ton seamless and seamed extruding machine, capable of producing profiles with cross-sections of up to 500 millimeters. This high-capacity press enables the manufacture of seamless aluminum ferrules, as well as customized large extrusions with consistent mechanical properties. After extrusion, profiles pass through a 13.5 meters aging heat treatment furnace, where strength and hardness are precisely developed. Dimensional accuracy is ensured using a 450-ton stretching machine and multi-axle straightening machines, which correct distortion and guarantee size precision. Cutting is performed on a 45-degree double-blade angular sawing machine, delivering fast production with accurate angular tolerances. Maximum product length reaches 6 meters. Surface finishing is handled in-house through a fully equipped anodizing plant, offering mill finish or a wide range of anodized colors. Quality control is rigorous, including physical material testing, hardness measurements, flatness inspection, and advanced 2D and 3D measuring systems. Environmental responsibility is integral, supported by an on-site wastewater treatment plant, ensuring sustainable and reliable aluminum extrusion production. Cutting steel, rolls, and coils with a Victor Oxy fuel torch represents a traditional, time-tested metalworking technique rooted in heavy industry. This old-school method relies on precise control of oxygen and fuel gas to generate an intense, localized flame capable of slicing through thick coiled steel. The process begins with secure positioning of the coil to prevent movement, followed by careful adjustment of gas pressures to achieve a stable preheating flame. Once the steel reaches ignition temperature, a high-velocity oxygen jet is released, oxidizing and cutting the material along a controlled line. Despite the availability of modern CNC plasma and laser systems, torch cutting remains widely used in scrapyards, shipbreaking, and maintenance operations due to its robustness, mobility, and low equipment complexity. Skilled operators play a critical role, maintaining consistent travel speed, correct torch angle, and uniform kerf width to ensure clean separation and minimize slag adhesion. Heat-affected zones are managed through experience rather than automation, reflecting a deep understanding of material behavior. This technique embodies practical craftsmanship, where efficiency depends on manual skill and situational judgment rather than digital control. Cutting coils with a Victor torch demonstrates how traditional methods continue to deliver reliable results in demanding industrial environments, preserving proven practices that remain relevant across generations of steelworking. Using a 5-foot Victor propane torch, the wheel cutting operation follows a controlled and methodical sequence to ensure safety and precision. Cutting begins from the bottom of the wheel, allowing gravity to assist slag flow while the steel is gradually opened toward the central axis. Once the cut reaches the axle zone, the torch is guided circumferentially around the axis at a thinner section, where material thickness allows faster penetration and cleaner separation. This circular cut weakens the structure and prepares the wheel for final division. The wheel is then fully separated into 2 equal halves with a continuous, steady torch pass. In the final stage, attention shifts to the axle itself. This traditional torch cutting method relies on operator skill, flame control, and accurate sequencing to handle heavy steel components efficiently. High-quality CNC oxyfuel cutting delivers precise results even on medium-thickness steel plate. This example demonstrates oxy cutting on 6 mm carbon steel sheet, achieving clean edges, consistent kerf width, and accurate geometry suitable for fabrication work. The CNC-controlled process ensures stable torch movement, controlled oxygen flow, and uniform heat input, minimizing distortion and reducing the need for secondary finishing. For metal bodywork and structural components, CNC oxy cutting remains a reliable, cost-effective solution that combines cutting efficiency with repeatable, industrial-grade quality standards. The QCC 4900 series powder cutting torch is engineered for extreme-duty metal cutting in recycling and heavy industrial environments. By combining oxy-fuel heat with controlled powder injection, the 4900 series produces an intensely concentrated, superheated cutting stream. This allows rapid penetration of thick, dense steel with excellent cut quality and stability. Designed for scrap yards, steel mills, foundries, and heavy metal processors, the QCC 4900 series delivers reliable performance, high efficiency, and consistent results on the most demanding materials. The Transformer Wound Core Cutting Machine Set FSH 350 from UPI is designed for the precise and efficient cutting of wound transformer cores used in power and distribution transformers. The system is engineered to handle silicon steel and other electrical steel materials with high accuracy, ensuring minimal burr formation and reduced magnetic losses after cutting. The FSH 350 integrates rigid mechanical construction with servo-controlled cutting units, allowing stable operation and consistent dimensional accuracy across multiple core sizes. Automated length measurement and synchronized feeding systems ensure repeatable cuts and uniform core geometry. The machine set supports high production throughput while maintaining tight tolerances, which is critical for transformer efficiency and noise reduction. Safety enclosures and user-friendly controls enhance operational reliability, while the optimized cutting process minimizes material stress and deformation. Overall, the FSH 350 provides a robust, production-ready solution for manufacturers seeking precise wound core processing, improved electrical performance, and consistent quality in transformer core fabrication. The CKW 4000 hydraulic forging press is a high-capacity open-die forging machine of the pull-down, two-column design, engineered for heavy industrial metal deformation tasks. It is configured to perform a broad range of open-die forging operations, including ingot upsetting, piercing, and deformation of circular or angular steel and non-ferrous workpieces, as well as mandrel forging of rings and hollow cylinders. The hydraulic cylinders are mounted in a fixed central crossbeam and act on a movable lower crossbeam, pulling the anvil toward the workpiece with controlled pressure and stroke motion. This arrangement reduces the overall press height above the floor while maintaining deep foundation support. The press structure includes robust hydraulic drive systems and long guides for the movable frame, ensuring stability and precision under high loads. Integrated sensors and computer control allow real-time monitoring of press motion, enhancing accuracy and repeatability of forged part dimensions, while advanced lubrication and closed-circuit oil systems support long service life and reliable continuous operation in demanding forging environments. Deep in Pennsylvania, inside a factory shaped by more than a century of experience, Shaw Barrels continues a manufacturing tradition that has quietly defined the accuracy of American firearms. For over 100 years, this facility has produced rifle barrels for many of the nation's leading gun manufacturers, making Shaw Barrels an unseen but essential contributor to countless firearms in use today. The process begins with raw material selection, multiple grades of high-quality steel, including 416R stainless and 4140 and 4150 chromoly alloys, arrive as heavy bar stock in various diameters. Each grade is chosen based on the final barrel profile and intended application. Automated cutting systems then section the steel into barrel blanks, cut slightly longer than the finished length to allow for precise crowning and final machining. This high-throughput operation produces a new blank every few seconds. From there, the blanks move into deep hole drilling, a critical operation that forms the initial bore. Using specialized machines capable of drilling multiple barrels simultaneously, a straight but undersized hole is drilled through each blank. The interior surface is still rough at this stage, requiring the next step: reaming. Reaming refines the bore diameter and surface finish, producing a smooth, mirror-like interior. Each barrel is carefully gauged using go-no-go instruments to ensure dimensional accuracy. Rifling follows, where the internal grooves that stabilize the bullet in flight are formed using a proprietary button rifling process. This operation introduces internal stress into the steel, which must be eliminated to preserve accuracy. Stress relief is carried out in large industrial ovens, where barrels are heated to approximately 1000 degrees Fahrenheit and slowly cooled under controlled conditions. Once stabilized, the barrels are machined externally to achieve perfect concentricity between the bore and the outer surface. Chambering is then performed, cutting the chamber and mounting hub in a single setup to maintain absolute alignment. The barrel now begins to take its final shape as contouring lathes form tapers or stepped profiles, depending on the firearm design. Optional fluting reduces weight and enhances heat dissipation, while sandblasting provides a uniform matte finish. Finally, in the custom shop, barrels are hand-fitted to individual receivers, head-spaced, test-fired, and inspected before final assembly. From raw steel to precision component, each barrel reflects a tightly controlled, in-house process where accuracy is engineered at every stage, an approach that has sustained Shaw barrels for more than a century. Within the Federal Ammunition Factory, technology, precision, and process discipline converge to form a seamless manufacturing ecosystem. Every operation is carefully synchronized, transforming raw materials into high-performance ammunition through a series of tightly controlled technical stages. Rimfire production begins with the precise forming of brass strip into cases, followed by the controlled preparation of primer compounds. These mixtures are carefully measured, pressed, and cured to ensure consistent ignition. Lead is melted under stable thermal conditions, then shaped and sized to produce uniform bullets and shot pellets with exact mass and geometry. Shot shell manufacturing relies on high-speed tube extrusion and head forming, where components are assembled with base wads and fed into automated loading lines. Powder charging, wad insertion, shot delivery, and crimping occur in perfect sequence, achieving both speed and repeatability. In centerfire production, brass cases pass through multiple drawing, annealing, and trimming stages to ensure structural integrity before precise bullet seating and propellant loading. Quality control anchors every step. Underground ballistic ranges measure pressure, velocity, and accuracy, while material analysis and terminal testing verify performance. This disciplined approach ensures reliability, consistency, and technical excellence in every round produced. Founded in 1993 under the Eastern Black Sea Firearms Production Project, TISAS has developed into a technically advanced manufacturer within the Turkish defense industry, specializing in handgun production and precision mechanical components. Production is based on an R&D-driven, flexible manufacturing system supported by proprietary design software, 3D modeling, and high-precision CNC machining centers. TSOS is uniquely positioned as the only private company in Turkey capable of cold-forged barrel production using dedicated cold hammer forging equipment, ensuring superior barrel strength, dimensional stability, and service life. All critical processes are performed in-house, including chrome plating, surface coating, and heat treatment. Dual heat treatment furnaces enable controlled processing of both standard alloy steels and high-hardness stainless steels. Manufacturing follows two core phases: design and production. Digitally modeled components are machined from analyzed raw materials, then subjected to dimensional inspection, heat treatment, marking, and coating. Final assembly is conducted per order, followed by rigorous functional and live-fire testing. Pistols are evaluated for feeding, firing, extraction, safety system reliability, accuracy, and performance under extreme temperature, water, mud, and angled firing conditions. This end-to-end technical control ensures consistent quality, durability, and operational reliability across TSOS's extensive handgun portfolio. The ammunition production line at the EAS Hymettus plant is designed for the high-precision forging of 155mm artillery shell bodies, a critical element in large-caliber ammunition manufacturing. At the core of the line is a 2,000-ton Yumuko hot forging press, engineered to deliver the extreme forming forces required to shape thick, high-strength steel into robust projectile casings with consistent quality. The process begins with material preparation, where selected steel billets are cut to length and heated uniformly in high-temperature furnaces. Heating the material to the appropriate forging temperature improves ductility and enables controlled metal flow during deformation. Once conditioned, the billet is transferred to the press and positioned within precision-machined dies. The Yumuko press applies successive high-force strokes, forming the external profile of the 155mm shell while simultaneously refining the internal grain structure. This controlled hot forging process enhances mechanical properties such as strength, toughness, and resistance to high internal pressures experienced during firing. After forging, excess material is removed through flash trimming, followed by heat treatment to achieve the specified metallurgical characteristics. Machining operations then complete critical dimensions, including internal cavities and interfaces required for later assembly stages. Repcon hot spinning technology is an advanced metal forming process used to manufacture large, thick-walled cylindrical and conical components with exceptional structural integrity. The process begins by heating a metal blank to a controlled temperature, increasing ductility while maintaining material strength. Under CNC control, the heated workpiece is rotated at high speed and progressively shaped over a mandrel using forming rollers that apply precise radial and axial forces. Hot spinning enables uniform wall thickness, refined grain structure, and reduced residual stress compared to conventional machining or welding methods. The technology is particularly suited for pressure vessels, rocket motor casings, artillery components, and heavy industrial parts where dimensional accuracy and mechanical performance are critical. By minimizing material waste and eliminating multiple weld seams, Repcon's hot spinning process improves reliability, shortens production cycles, and delivers repeatable quality for demanding aerospace, defense, and energy applications. At Navantia's Cartagena Shipyard, the floatout maneuver of the S-81 Isaac Pearl submarine represents a highly controlled naval engineering operation marking a critical milestone in the S-80 program. The maneuver begins with final structural inspections, sealing verification and validation of hull penetrations, ensuring full watertight integrity. Dock gates are closed and the dry dock is gradually flooded in carefully monitored stages. Ballast conditions, trim, and stability are continuously calculated in real time to maintain uniform load distribution and avoid hull stress concentrations. As water levels rise, the submarine progressively transfers weight from the dock blocks to buoyant support. Engineers monitor displacement, draft, and longitudinal balance using laser alignment systems and sensor data. Once full buoyancy is achieved, the S-81 is gently released from its supports and stabilized using mooring lines and auxiliary handling systems. The floatout operation is executed at extremely low speeds to prevent dynamic loading or uncontrolled movement. Tug assistance ensures accurate positioning within the basin. Upon completion, additional checks confirm hull behavior, structural response, and system readiness. This maneuver demonstrates Navantia Cartagena's expertise in submarine construction and complex naval operations, validating the structural integrity and engineering precision of Spain's most advanced conventional submarine platform before the start of harbor trials. HMAS Waller's full-cycle docking and undocking represents a critical phase in the Collins-class submarine lifecycle. During a full-cycle docking, the submarine is carefully brought into dry dock for extensive inspections, structural repairs, system upgrades, and component replacements as part of a long-term overhaul, typically occurring every 10 years and lasting up to 2 years. Precision dry dock positioning and support platforms ensure safe access to internal and external systems. Technicians carry out hull maintenance, equipment modernization, machinery overhauls, and structural enhancements with rigorous quality assurance and system testing. Undocking is equally meticulous. The dock is gradually flooded, buoyancy and trim are monitored, and the submarine is guided out under power or tug assistance. Once clear, final system checks confirm full operational readiness, returning HMAS Waller to active service. At SolidCAM TZ Schramberg, high-performance machining demonstrates how advanced CAM strategies and HPC cutters redefine modern manufacturing efficiency. The process focuses on the precise machining of complex components, using high-performance cutting tools designed for maximum material removal rates and extended tool life. Through optimized toolpaths generated in SolidCAM, HPC milling cutters maintain constant tool engagement, reducing vibration and thermal load while enabling aggressive cutting parameters. This approach allows higher feed rates and deeper axial cuts without compromising surface quality or dimensional accuracy. Adaptive roughing strategies ensure stable chip formation and consistent load distribution across the cutting edges. The result is a highly efficient, repeatable production process that reduces machining time, lowers tool wear, and increases overall productivity, showcasing SolidCAM's capability to support demanding industrial manufacturing applications.